Hello, hope you're having a great day today. We are going to take a look at section 1-3 in our trig. And where we're going in this chapter ultimately is we're going to start solving equations with trig functions in them. And a lot of people find this challenging. So what I've done over the course of this chapter is I've broken that process down into little chunks. So what we're going to do today is just simplify an expression, not solve an equation. We're just going to practice manipulating the trig functions. They follow the same algebra rules that the x's and y's do in general, but just learning how to identify the different patterns and forms. And then hopefully, as you get good at that, if you stay up with your homework, when we get to the equations, it won't be as big of a chunk to bite off. So, in review, we have defined sine, cosine, tangent, cosecant, secant, and cotangent in terms of x and y being a coordinate on the unit circle. So if we have our triangle here, our coordinate is x and y. And we talked about that because this is a right triangle and how the trig functions are defined, and the hypotenuse being 1, that this is the x component of that coordinate, this is the y, but it turns out since the hypotenuse is 1, this is also the cosine of theta, if this is our angle. And this ends up also being the sine of theta. And so that's how we came up with these formulas in the box. I'd like to lay out another way to look at these trig functions, and it's a simple substitution between the cosine being x and the sine being y. So it's not a super complicated jump. We're just going to define sine as sine. It stays. It's like our basic building block in trig. Sine and cosine are like the basic building blocks. You're playing Legos and they're like the 6 top bricks. Like that's what builds everything, okay? And tangent now, instead of looking at it as y over x, I'm going to define it as what is y? Well, y is sine. So tangent is sine over the x value, which is cosine. Okay? Similarly, we can say that cosecant, it's 1 over y, but y is sine. So this is 1 over sine. And I think that you already kind of intuitively knew this. I've always said that cosine is sine flipped over. So that's exactly what this says. Secant, similarly, is 1 over cosine. And cotangent is cosine, the x value, over the y value, which is sine. Okay. What I want is, in your brain, I want you to be able to identify these things in a multiple of ways. For example, when I think of tangent, I can say tangent is opposite over adjacent if I'm looking at a triangle. If I'm looking at the unit circle, I think tangent is y over x. And now, if I'm going to solve an equation, I think tangent is sine over cosine. So there's different contexts where each of those definitions is helpful. And I want you to be able to flip back and forth between all three of these. That's why it's important to memorize, so you're not shuffling through papers every time you're in a different context. All right, so that's our first setup. That's how we're going to look at trig functions today. The other thing that I want to redefine is the Pythagorean theorem. So we looked at this in the last video in terms of a right triangle. So here's my right triangle. This is my A, this is my B, and my C, and the Pythagorean theorem says that A squared plus B squared equals C squared. Well, let's look at that in context of the unit circle over here. Here's a triangle. I'm going to look at this triangle right here. Okay. And this is my A side, this is my B side, and the hypotenuse is always my C side. So in terms of trig functions, I can write this triangle in the unit circle like this. A squared, which is my cosine side, plus B squared, which is sine, my sine side, equals the hypotenuse squared, and 1 squared is just 1. So this is the Pythagorean theorem for trig functions. A couple things to note with the notation. When we put a squared on a trig function, we put it between the trig function and the angle. The reason is because if you write cosine of theta squared like that, then I think that the angle is squared. And what this means in the Pythagorean identity is I want you to take the cosine of theta and then square the whole thing, not just the angle. Okay. The other way you could write this, if you chose, is to so this guy is not the same, but this one is. If you want to, you could put parentheses around the whole thing and square it. This is the same. This one is the same as this one right here. Okay. Typically, we write the squared in between the trig function and the angle, though. Now, I want to do an algebra manipulation with this equation. I'm going to take this one, I'm going to write it out on the side, so this is one of our trig functions, or I mean our Pythagorean identities. Now I want to take this function and I want to divide it by cosine squared. Now that might feel like magical to you. Why did we decide to divide it by cosine squared? Just because I know what's going to happen. There's no, I wouldn't expect you to think of doing that ahead of time. It's just something that I'm going to show you what happens when you do that. It's legal because in algebra, as long as you do to the left, you can do to the right. So I divided everything by cosine, so it's still equal. And now let's reduce this. Cosine squared theta over cosine squared theta, well, that's 1. And sine squared over cosine, well, look back up here at how we defined our trig functions. Tangent is sine over cosine. So if I square the top and the bottom, it's still, the ratio is still equivalent. We are going to get, except it's going to be a tangent squared. Okay, everything's just squared, which is also legal in algebra. In addition, on the right here, I have 1 over cosine squared. Well, if you just square both sides of this situation, you get 1 over cosine squared, and that is going to equal secant squared. So by dividing by cosine, I actually get this second Pythagorean identity. There's going to be 3. And I'm showing you how to figure them out. Okay? The way that you figure out the third one is you take your original Pythagorean identity, just like we did in the previous example, except instead of now dividing by sine squared, I'm going to divide, or by cosine squared, I'm going to divide by sine squared. I have to do that all the way across the equation to keep it equal. And let's see how this reduces. Cosine over sine, look back at your trig functions up top. Cosine over sine is cotangent. So since it's squared, it's going to be cotangent squared. Sine over sine, well, that's 1. And 1 over sine squared, well, that's cosecant squared. And this turns out to be our third Pythagorean identity. Now, you have a choice. These are very important. You will use them a lot. In this class and in calculus. You can memorize them all if you choose. What I choose is I remember that the last 2 were created by dividing by cosine and then sine. So I actually only memorize the first one, and then I figure the other 2 out at the beginning of my homework set and write them at the top of my page. You can do either one, however you choose to proceed. Okay, so these are the formulas that we're going to use today in solving our, simplifying our expressions. So I'm going to cut these out and I'm going to pull them down here so we can look at them as we're doing problems. Okay. And erase the guys that came along for a ride there. All right. So here's your game plan for these homework problems. You have options. The first option that you can do when simplifying an expression is rewrite everything in terms of sine and cosine. So that would be done using these formulas. Using these formulas up here. That's one thing that often works. The second thing that you can try is to add fractions. Yep, we never get away from it. You thought you were done with logarithms, but no, they're back. Okay? Sometimes adding fractions causes things to simplify, cancel, fall out. The third thing that sometimes happens is you can factor something. And the fourth option is using the Pythagorean identities. Okay, so the way the Pythagorean identities will work is that you can substitute one side of the equation for the other. So for example, if I had a problem that had a secant squared in it, instead of secant squared, I could write 1 plus tangent squared. See, I'm swapping one side of the equation for the other side of the equation. And that's how we'll use those. I'll show you in an example later. Okay, so let's jump right in. Here's our first example. I'm going to try to do several of these. They are challenging at first till you get the hang of them. The trick with these, guess what? Practice. No big surprise there. Okay, and the directions on these guys will all say simplify. And for the most part, these problems are written so that they drop down to something like super magical, and like everything, you'll do one thing and everything will cancel out. That's how you know you finish the problem. Okay, if nothing magical happens, keep going, try some things. Now, my game plan is these steps, and you can do these. There's no order, there's no formula, which is why it can be hard for people. You just pick one and try it. And if it doesn't work, then you pick something else and try it again, okay? And you have to not be afraid in these problems of erasing and starting over. That is going to be your bread and butter, is just being able to say, well, that didn't work. I'm going to try something else, okay? So in this first problem, because it's just one fraction, and I don't see anything to factor, and I don't see any Pythagorean identities, I'm going to try the first option, which is rewrite everything in terms of sine and cosine. So cosine, well, that's just cosine. That doesn't get rewritten. It's my building block, okay? Secant, though, secant is 1 over cosine. So this is going to be multiplied by 1 over cosine x. So I'm substituting the secant x for my 1 over cosine, and that's using this equation up here. And then I'm going to divide that by the cotangent, but instead of the cotangent, I'm going to write cosine over sine. And that's also using this equation up here. So I'm substituting this for that. See how that's working? And then you're just going to do a little bit of algebra. Sometimes things multiply, cancel out. So this cosine up top is actually over 1. And if you notice, they multiply, fractions multiply straight across. So this becomes cosine over cosine, which is 1. These guys cancel, in other words. This is going to be 1 over cosine x over sine x. Oh my gosh, we've got a fraction on top of a fraction. That is also never going to go away. So what do? Hopefully you know by now. You take the denominator, you flip it over, and you multiply on the top and the bottom. So these cancel out, and I'm left with sine x over cosine x. Okay. And then sometimes in this, using this method, this rewriting everything, it's nice to then look back at your theorems or your equations up top and say, now could I write that simpler? And I go up and I say, oh, let's see, there's this right here is tangent is sine over cosine. So I can write this as tangent x, and that's done. Typically when you get down to one trig function, it's done. Okay, so that's how the idea of number one works. I'm going to walk you through an example of each of these ideas, and then when you're approaching your homework, you will have seen each of them. So let's do another example. I'll just scroll back up if we need the formulas, okay? Let's look at sine x over 1 minus cosine x minus cosecant x. Okay, there's two ways to approach this problem. One is that I notice that I have two fractions. I mean, this is a cosecant's a fraction, it's over 1. I have two fractions and they're subtracted, so I could actually perform that operation. That's a great idea. I also have a cosecant, which can be written as 1 over sine, and that's also a great idea. It does not matter which one you choose or which one you do first. So I'm going to rewrite in terms of sine and cosine first. This becomes 1 over sine x. Now this is why the memorization is really helpful. If you keep having to scan through your formulas while you're doing this, it's going to be a hard process for you. But if they're already in your brain, when I see cosecant, I see 1 over sine. If you have that memorized at the front end, this will radically improve your success on these problems. Okay, so put them on note cards and just memorize them right now, okay? We're going to add these fractions. When we add fractions, we need common denominators. So that means over here, I need to multiply by 1 plus cosine, or 1 minus cosine on the top and the bottom. And over here, I need to multiply by sine on the top and the bottom. All right, so my top combines here. I'm going to get sine times sine, which is sine squared. And then I've got a minus sign in between, and I've got 1 times this. So this is going to be 1 minus cosine x on the top, all over my denominator. Okay. Now, here's how the Pythagorean identities work. Anytime you see a squared on a function, that should make you think Pythagorean identities. That's how you know that's going to come into play, okay? So let's write this identity down. Sine squared plus cosine squared equals 1. That's my first Pythagorean identity. And if I want to use that, I look at what's in my equation. So I've got this pink circled sine squared, and then I go over to my Pythagorean identity and I circle that and I get that by itself. So over here, I'm going to subtract cosine squared x. So what that helps me to understand is sine x is going to be 1 minus cosine squared x. Now this is what I can substitute in to my equation. So now I'm going to go over here and say instead of sine squared, I'm going to write 1 minus cosine squared. Okay, so that's my substitution. And this minus sign is going to hop in up top. So this is going to become a minus 1 and a plus cosine x, all over sine x, 1 minus cosine x. Now, why am I doing that? Why am I continuing? Because nothing magical has happened yet. Okay, I'm waiting for something magical to happen where everything cancels out and becomes super simple. Okay, so that's why I'm continuing on. Do I know this is the right path? No, not necessarily. I'm trying some things, I'm substituting things, I'm multiplying stuff out, and hopefully I get lucky at some point and something happens. Okay? So let's keep going. I look at this equation and say, well, there's a 1 and a -1. Those cancel. Okay. And so on the top, I've got a cosine squared, it's negative, and a cosine x. And ultimately, my goal is to cancel. The only way you can cancel in a fraction is if things are factored. Well, the bottom is factored. It's two things multiplied. The top is not. So maybe I want to think about factoring that. Let's see. The first thing I think of when I think of factoring is there a greatest common factor? So do these two terms have anything in common? Oh, yeah, they do. They have a cosine in common. So I'm going to pull the cosine out. And in this term right here, I've got two cosines. That's what cosine squared means. So when I pull one out, I'm left with 1, and I'm going to keep that negative sign in there. And in this second term, when I pull a cosine out, there's nothing left. So remember, there's an imaginary 1 in front of here. So the 1's going to hold the spot. Okay, now I'm uncomfortable with that negative sign in front. It's just not standard form. So I'm going to rewrite that a little bit. I'm just going to flip the order of that. This is 1 minus cosine x. Just put those in different order. And now look at what happens. Oh, okay, now they're both factored. Now you can cancel full factors. So I see things that match. This is exactly the same as this. And because this is multiplication, because they're factored, that's legal. And I'm just left with cosine over sine. And that's better known as, I'm gonna scroll up here and look at my trig functions. Oh, let's see, cosine over sine right here, that's cotangent. Okay, so that means this is going to be cotangent x. And that was the magic I was waiting for to happen. Now, I love this example because it uses like 3 of the suggestions. So let's walk back through it. The first part is I get a common denominator and I add my functions together. The second part is I take this Pythagorean identity and I plug it in. And then the last part is I factor and cancel. That's a very standard pattern that you'll see in these problems. Okay, so what I encourage you to do is stop the video, rewind, and try it yourself without looking. That's how you practice. Okay, I'm going to go on to the next problem. Let's do 2 plus tangent squared over secant squared minus 1. Okay, again, when I'm looking at what to do on this problem, I'm seeing two things. First of all, I'm seeing that I have several squared terms right here. That says Pythagorean identity to me. So when I go back up to my Pythagorean identities, I'm looking at these guys in the box, and I'm especially noticing that this middle Pythagorean identity has tangent and secant in it. When I have an equation that has 2 of the Pythagorean trig functions that belong to each other in a Pythagorean identity, that's a good sign that that's going to be a helpful thing to do. The other thing that I notice in this problem is that I've got 2 fractions. So I've got some options. I could substitute some of those green trig functions out with Pythagorean identities, and I could also subtract fractions. And probably both of those will get you to the end. It doesn't matter what you try. But if you get stuck in a pit, you just cross it out and try a different trick. But those are the 2 things that raise red flags for me. Okay, so here's what I'm going to do. I'm going to take the Pythagorean identity, tangent squared plus 1 equals secant squared. Okay, that's my identity. And I'm looking over here at, I'm going to choose to substitute the tangent. Now, why did I choose the tangent? No special reason. I could have substituted out the secant as well. I'm just choosing that one. A lot of times I like to substitute into the numerator of a fraction rather than the denominator, and I'll show you why a little bit later. So that means that I have to come over here. Whoops, there's supposed to be an x right there. Sorry, x. I'm going to come over here and I'm going to circle what I have in my equation. I just have this tangent squared x and I'm going to solve for it. So I'm going to subtract the 1 over. So that means that I can take the secant squared minus 1 and I can plug that in right here for my tangent squared x. So here we go. 2 plus secant squared x minus 1 all over secant squared x minus 1. All right, when I look at my fraction, well, let's see, I've got 2 minus 1 on the top. So I'm going to combine those guys. 2 minus 1 is 1 plus secant squared x over secant squared x minus 1. Now, nothing super magical has happened yet. So I've got two options. One is I can take this 1 and get a common denominator and add these guys. That's a great idea and it will work. Okay, but I want to show you a different trick. And one of the reasons I like to substitute into the numerator up here, we went into the top of this fraction, is because if you only have one term underneath a fraction, you can split this up into two fractions. This goes under the 1 and this goes under the secant squared x. And it can get you out of fraction land without actually adding the fractions. Here's how it looks. This becomes 1 over secant squared x and secant squared x over secant squared x. So the rule is you can split up a fraction if you put the whole denominator under each term. And if there's only one thing on the denominator, this is really beneficial. Now let's reduce 1 over secant. Okay, what happens when you flip secant? Well, when I flip cosine, I get secant. So it then follows that if I flip secant, I get back to cosine. So this is cosine squared x. Secant over secant, well, that's 1. And then I've got this minus 1. Oh, those 1's cancel. And I've got cosine squared x. That was the magic that I was waiting for. Now, could you have added the fractions instead of breaking up that fraction? You bet. And it probably would have worked out, and well, I know it would have worked out, and you would have gotten the same answer. So there's many paths to the answer, and when we answer questions in class, I'm going to try to ask you what direction you feel like you want to go so that I can go down your path and not the path that makes sense to me. Everybody's brain functions differently and you see different things. So that's really important that you kind of be true to what your instinct is in these problems. I'm going to show you one more, and then I'll let you guys do some practice. The thing we haven't really stepped into is factoring. Whoop. All right, let's look at this guy. There's no fractions in this problem, so adding fractions is not an option. Everything is in terms of sine and cosine, so rewriting doesn't help in this situation. There is an option for a Pythagorean identity. Okay, right here I have a squared, and that does speak to Pythagorean. But because there's nothing for it to cancel with, I question that move, if it will be helpful. So the only other thing left on my list is factoring. So then I start looking for my factor patterns. We've worked on this quite a bit. And what I see right here are even powers, and I see a subtraction sign. This is a difference of two squares. So in algebra, you saw this pattern like this. And you said, oh, this is x squared and this is 4 squared. So it factors as x minus 4, x plus 4. Well, this doesn't have to be a 2 up here. It could also be a 4th power, in which case this would factor as an x squared minus 4 and an x squared plus 4. Okay, and that's the idea of what's happening here. I have something to the 4th power minus something to the 4th power, so when I split them evenly, I better write as I go, I get a sine squared in each quantity, and I get a cosine squared in each quantity. So this one is splitting up here and here, and this guy's splitting up here and here. And just like the pattern over here, I alternate plus and minus. Okay, and I've got, don't forget your purple on the end there. Sorry, I'm going to shift this over a little bit. I've also got a plus cosine squared. Okay? Don't want you to look back on this and get confused. Okay. Now what do you see? I see Pythagorean identities in spades. I see lots of squareds. And this is the one that I really want you to see every single time. Okay? Because it's the easiest way to reduce something. Sine squared plus cosine squared equals 1. That is a Pythagorean identity, and this is 1. All right, so here's what I'm left with. The 1 goes away because it's being multiplied by this, and multiplying by 1 doesn't do anything. So that's what I'm left with. And that was kind of magical, but it still looks a little complicated. Maybe there's more that I can do. I'm hoping that you notice this. Look at that. That's a difference of 2 squares again. And this will factor like sine x plus cosine x and sine x minus cosine x. Whoop, cosine squared x. Okay, that was cool, but that didn't really do anything for me. And I walked myself deliberately into this little hole because I want you to see what it looks like. I think it's really important that you see that, okay, that factored and that was accurate, but it wasn't helpful. Because now nothing cancels. There's no Pythagorean identities in here because I don't have any squareds anymore. So I don't want to do that. And then I go, well, maybe I missed something else up here. I go, oh, wait a minute. I was so focused on factoring this part that I missed this part. Do you see how that happens? And that's super common. That's fine. What's going on here? Oh my gosh, I've got a cosine squared minus a cosine squared. They cancel. So I'm just left with sine squared. So I go back here and I say, okay, this step wasn't helpful. No problem. And I'm left with sine squared, and there I am. So it's super easy to be focused on one part of the equation and miss like the cancellation over on the other side. That's okay. You just back up a step and try something else. I can't emphasize this more, and I really, I will try to do this in class face-to-face, but I cannot emphasize how this chapter is about volume of practice. The more that you do these problems, the easier that they will be. And they are hard for people because they're hard. They're hard, and people don't like to fail and start over. That is uncomfortable. That is exactly how you learn. So I need you to try. I need you to try and fail and try again, fail again and try again. And I guarantee if you run out a problem 2 or 3 different ways, you will get it. Okay. And once you get it, then the next day try it again and see if you see the pattern or the plan a little more readily the second time. Okay. Time spent now will really benefit you at the end of the chapter. So I encourage you to do that. And this is the end of section 1-3, and you can do the worksheet now that will be posted in Canvas. Have a great day.